So, good afternoon. I'm sorry, I'm really sleepy. So today I'm going to briefly talk about some of the ongoing work I'm pursuing with my younger colleagues here and other places. This is about modeling gravitational waves from black hole binaries, not necessarily in eccentric, but also hyperbolic and non-bound orbits. So these are the collaborators. I mainly work on these topics. Sushri Tiwari, Abhimanyu, Lankesha, they are graduate students here, along with Shubhajit, who recently joined my group. Maria and Gihuk used to work, we still work a lot on this aspect. They are postdocs in Zurich and Desi, Shashwat, and of course, I have some senior colleagues too. Okay, it seems I can't go to the next one now. Okay, so this will be the rough plan. I will give a rough introduction to waveform modeling, and I will try to convince you that eccentric black hole binaries are somewhat interesting to the current observatories and the one we are planning to launch in the coming years. And I will talk about our efforts to actually model ready-to-use time and Fourier domain templates. And also I will briefly mention about what we have in the collaboration called the Hyper-E effort, and briefly touch upon its implication for nanohertz gravitational wave astronomy that hopefully will be inaugurated in next year or so. Okay, so that's roughly the motivation, because the gravitational wave data analysis, especially the searching for gravitational waves as well as extracting parameters of observed signal, requires you to have what you expect from general relativity. So it's a bank of templates, and it's good to have them to available for your analysis in a very computationally efficient way. And so this is the idea of modeling these sources for extracting information about the events from the LIGO detectors. So we are interested, obviously, if you're looking at the compact binaries that are interesting to the ground-based observatory, we are interested to look for signals from neutron star, black hole, or black hole neutron star binaries. And the current observatories are mainly look for binaries in the circular orbits. So they have three stages of the coalescence. What we are familiar with, you have the slow in spiral, which due to the emission of gravitational waves, where the velocities are comparable to a fraction of that of light. Then you have the rapid merger and followed by the ring down. And the merger and ring down parts are considered to be the strong field domain as far as the general relativity is concerned. And the early in spiral can be sort of modeled using post-Newtonian approximation to the general relativity. And these days, there are routinely observation of such gravitational wave even from compact binaries. I'm just flashing one of the catalog created by Karan and his collaborators. So when you look at the post-Newtonian approximation, so they essentially provide you corrections which are general relativity based to the Newtonian dynamics, and the game is to actually compute the equation of motion or orbital dynamics that can be purely the equation of motion, or if in the case of spinning binaries, the equation to talk about the spin of the black hole and its coupling to its companion. And then, of course, you need gravitational wave polarization state, H plus and H cross. There are two in GR. Then how they temporarily evolve with time, that requires you to actually have orbital frequency evolution. And so why they are required? Because if you are interested in the detector response, that's what you're going to do when you analyze the data. That's essentially given by h plus t times f plus time plus f cross times h cross. F plus and f cross are the antenna pattern. They are going to be essentially stationary for the scenarios we are interested. So the temporal evolutions are essentially going to come from h plus and h cross, and this is how you have to model. And since you are going to cross correlate your signal with the expected signals, it's better to do this in the Fourier domain. And so it's easier if you have the templates which are easy to implement in the Fourier domain. So what we do is that we actually compute, especially in the Poisson-Newtonian approximation, you create a time domain signal and compute its Fourier domain analytically using so-called the stationary phase approximation. I'm not going to go into the details. So the crux of the matter is that if you have a signal characterized by an amplitude s of t and a phase phi of t, then and if you can actually compute its Fourier transform if it satisfies certain conditions, and that expression is given by phi. So the point is that you have to evaluate these quantities, which I actually show there at the stationary point, which is essentially given by if you have the orbital phase varying, so then the Fourier frequency will be just given by j times that f, which is the orbital frequency. So this comes from the stationary phase approximation. And this can be implemented. For example, the current searches for non-spinning black hole binaries uses something called phenom-D, which is a phenomenological IMR in spiral merger ring down h of f. And so the in spiral part actually comes from the Poisson-Newtonian accurate description based on such stationary phase approximation. But those are for the circular. Now we are interested in the eccentric binaries. So they are plausible sources of gravitational waves. Why are they interesting? Well, if you can pick up or constrain orbital eccentricity of gravitational wave events, they can actually tell you about where they come from, how they are formed. And right now that's sort of problematic. And there are many possible channels through which actually the black hole binaries that LIGO regularly sees can be created. So they can be globular clusters, they can be in young or open star clusters, they can be in active galactic nuclei. I'm going to give some of those references. There are plenty of papers in the literature. And especially when you have dense stellar neighborhood, it's actually possible to have formation of so-called hierarchical triple, and that can lead into so-called the Cosine-Lido mechanism, which can actually boost eccentricity. So in principle, several events are possible per year. In fact, there is a clear possibility that one of very interesting gravitational wave event 19/5/21, which was announced last year, can actually come from an eccentric black hole binary merger. There have been a number of papers in that direction, even though the standard LIGO-Virgo collaboration paper argue this as a merge. It's a short duration signal around 0.1 second. It has only a few gravitational wave cycles restricted to a very narrow frequency band, 30 to 80 hertz. So if you consider them to be quasi-circular, and assume them to be sort of comparable masses, then it can be 85 to 66 solar mass merging to form 142 solar mass final remnant. But there are other interpretation, and many interpretation actually. They have been listed there by Gayatri, then from friends in Australia as well as from Hanover. Okay, so I'm sorry, So why it's interesting to look for why do you need to actually construct eccentric signal, though you are able to actually capture them with circular binaries? The reason is it's if you actually search possible eccentric signal with circular one, there's a clear chance that you may actually miss them. That may not be the case for such a short duration, but if you have a longer duration signal, and they are usually explore so-called certain faithfulness criterion. And the game is that you don't want to have signal your template uh, with some faithfulness which is 0.97. And so you can see that if you have binaries in 10 solar masses and all that, if you have small eccentricity, it can go well beyond that faithfulness criterion. So it's a good to have extension of the quasi-circular templates. And so our motivation is so this is a kind of a cartoon of such an eccentric waveform created from purely numerical relativity simulations. Uh, so our game is to actually create IMR waveforms either in time or frequency domain, which are useful for moderately eccentric systems like 0.4 or so. And I will just go back to kind of remind you that such analytic inspire. So the crucial part is the inspiral part where the eccentricity effects are going to be dominant. So I want to contrast you why this is sort of going to be a slightly more detailed. So if you're going to consider just the so-called the restricted first Newtonian templates for the circular binary. So this is called the Taylor F21, and what you have is that expression given in 9. So it's purely analytic. So everything can be actually written down. You only need to know a quadrupolar order expression for H plus and H cross, and how the orbital frequency changes because of the emission of gravitational wave. Then you can actually compute that fully analytically. And so there were efforts to extend this to eccentricity. So this was pursued by Nico and his collaborator, Nico Yunus, roughly 12 years ago. So what they did was they actually used the Newtonian H plus and H cross, and they give a quadrupolar order. So that's the dominant order effects of gravitational wave emission on how the frequency and eccentricity varies. And they came up with this purely analytic expression for the template for eccentric binaries. And this was extended while considering radiation reaction effects to higher post-Newtonian order. So those are the expression. They are lengthy, but they are analytic in nature. However, there was a problem with this computation. That is something to do with general relativity. So in general relativity, as soon as you bring in eccentricity, it's actually fairly straightforward to argue that your orbit will not close onto itself. This has nothing to do with the gravitational wave emission. It's a purely so-called conservative effort. And we know this is advanced of periastron or perihelion or periapsis. There are various names for it, where you're looking at the system. And essentially because of the fact that your potential is no longer 1 over r, and then the system cannot allow a closed eccentric orbit, so it will precess, and this can be characterized. And so now you need to incorporate that effect before you worry about effect of gravitational emission. And so that was pursued by Sashi Tiwari and collaborators. So what we provided is an expression for the Fourier domain h of f. So the gravitational wave, so the response function in the Fourier domain because of the gravitational waves emitted at the quadrupolar order by black hole binaries moving in the precessing eccentric orbit. So what you immediately find is that the harmonic structure is changed. Again, this is fully analytic. I'm not going to get into the details. So you actually find that the harmonics are not emitted at multiples of orbital frequency. There's a clear periastron advance influence split and shift of the harmonics. And so this was computed, and this effort was actually required to use an earlier work by another graduate students from our group, Yannick and Abhimanyu, where they actually use the sophisticated Keplerian type parameterization, finding its analytic solution to give you the time domain signal, which can be used to compute the Fourier domain expression. Anyway, so then just want to convince you that what Srishti provided was this fully analytic templates for eccentric binaries, where they incorporated the effect of orbital motion, advance of periastron, and the gravitational wave emission. And this is fully analytic. It's a fairly detailed and lengthy calculations, and a clear prescription where those expressions will have to be evaluated. That's going to depend on the kind of eccentricity and the mass you have for the system, and they are being incorporated into the software for doing analysis. So again, in order to see whether the effect of advance of periastron is going to be relevant or not, we did some preliminary analysis, not to confuse with anything detailed. Again, the computing is essentially an overlap integral between two waveform families. They are kind of maximized over certain parameters, and the game is that maximization, which is normalized to 1 if they agree with each other, but you would like to have them above 0.97. And what we find is that the advance of periastron effect starts coming in when you have this is for kind of stellar mass black holes around 0.3 or something like that. And that's sort of important, where we think these efforts are going to be relevant when you're trying to model these things. I'm going to skip this. So that, and then she went on to actually compute certain versions of this waveform, which sort of useful for moderately high eccentricities too, influenced by certain efforts from Nico and his collaborators. So these are the papers. I will not go into the details any further. Okay, so what's going on here? So we think we have computed, and in this detailed manuscripts, amplitude corrected in the sense that they are not quadrupolar order anymore, a Fourier domain waveform for black hole binaries in spiraling along general relativistic eccentric orbit, and you can tolerate eccentricities say up to 0.4 or something like that. So the important thing is the effect of advance of periastron have been incorporated into this. I have been collaborating with Maria and Hane and her collaborators Sasha and others to incorporate to create an IMR waveform in the Fourier domain, the phenomenological one, especially trying to get inputs influenced by the paper by Tony and his collaborators. And hopefully these efforts are going to complement already existing waveform families by Alessandro Nagar and Frank Ohm and others. So that's ongoing, and we have also incorporated the effect of spin in another effort. I'm not going to get into that. Okay, so but that's in the Fourier domain. So we thought about doing this in the time domain for certain reasons where we don't have any constraints on the eccentricity. So there's already an effort. I mean, there are a few efforts in that direction. So we were influenced especially by an effort by Ian Hinder and his colleagues, as well as by Herta, which involved Prayush, I presume. So the game is that you have a time domain post-Newtonian accurate spiral waveform. You try to stitch it to a merger waveform that usually arise from interpolating a number of numerical relativity waveforms. In many of these efforts, they consider quasi-circular numerical relativity waveforms. So that's the game. And again, there's a detailed way of constructing time domains eccentric signals. So this was influenced by detailed papers from Damur, Iyer and I and my students. So the game is that H plus and H cross, we try to write it in terms of, they are in general orbit. So they have R dot, phi dot, and then trying to bring in the eccentricity. What we do is that we use something called Keplerian parameterization. I'll show you what I meant by that later. And then you incorporate, so that's what this expression U comes in. So that's called the eccentric anomaly. This is associated with Keplerian parameterization, and it's a post-Newtonian extension routinely used in pulsar timing, and these days even for the PTA signals. And then you connect that U to time. That's the, you need to worry about a transcendental equation, and it's actually post-Newtonian expansion of that. Then you incorporate effect of gravitational wave emission into that. So that's the algorithmic way of tackling this. The details can be horrendous. And that's precisely what Gihuk and Shashwat are doing these days to model in the time domain in spiral merger ring down waveform. The paper should be submitted very soon. So what's more interesting is that so what Ian did was to actually couple eccentric orbits which are moving along so-called the third post-Newtonian accurate orbit, influenced by gravitational wave emission effect at the second post-Newtonian. We went ahead and did the conservative part of the 4 PN order, incorporating the gravitational wave emission at the third post-Newtonian order. You can see that that actually introduces changes. So we are actually exploring what's going to happen because of that. So one of the crucial element is precisely this. This is the Keplerian type parametric solution. So if you look at this equations 24, so the Newtonian part does not have C's. So everything else is because of general relativity. And so this requires detailed computation and it's checking and all that. So it's been incorporated all that. So hopefully this is will be incorporated, and then we will try to stitch eccentric mergering down to that in the coming years, and hopefully that will happen in the near future. Okay, so
Gopu, you have 4 minutes.
Okay, this will be done very soon. Okay, now so we are also shifting our attention to hyperbolic events. There are a number of reasons for that. There is an hyperactivity in the LIGO collaboration, and the pulsar timing arrays are very much interested in such burst signals. So, so the game is to actually come up with, in general relativity-based hyperbolic passages. And this was done by Gihuk during his PhD times. So what I actually show is the hyperbolic passage of two compact objects. So the black one is essentially the Newtonian, and the red one is the post-Newtonian. You can actually see that the one, so periastron actually turns the orbit around. So you get associated signals, and they are it's quite detailed. And again, that requires us to derive this Keplerian parametric solution. It's for the first time this is done without using so-called analytic continuity. It's kind of interesting exercise in itself. And so they are being incorporated, and hopefully all this O1, O2, and O3 data sets will be searched for such events, but that's not really done here, mostly done by Shubhanshu, Maria, and their collaborators with inputs from us. Okay, we are definitely getting into international pulsar timing array efforts to detect nanohertz gravitational wave in big way. So that's Indian pulsar timing array. Our PI is Balchandra Joshi. So this discovery hopefully will happen in the next year or so. We'll have contribution from Indian data, Indian analysis tool, and of course some theoretical efforts. And so we actually hosted IPTA meeting, the last in-person meeting during 2019. And there are, of course, we will be constraining supermassive black hole binaries in eccentric orbits, and also their background influenced by eccentricity. These are ongoing efforts. So they are essentially led by Abhimanyu, Loki, Shubhajit, and others. So again, both whatever we have done for the gravitational wave templates have been adapted, and they have been incorporated into Enterprise and Tempo 2 and things like that. And hopefully that will be so. But our focus is on slightly different. We actually want to create a source that can do persistent multi-messenger nanohertz gravitational wave astronomy, especially during the era of square kilometer array, NGEHD, and IPTA, matured IPTA. And there are lots of work on that direction. I will hopefully that can happen in the next decade or so. Okay, so that's essentially what I want to. So the summary is that we are pursuing a number of investigations, essentially influenced by maturing hectohertz gravitational wave and the nascent nanohertz gravitational astronomy. Thank you very much. I will be happy to take questions.
Questions? Can you use the raise hand option, please?
May I ask a question? This is Indranil.
Yes.
Hi, Gopu.
Yeah, please go ahead.
Yeah, so one clarification, one question. The clarification I need to ask is that you showed the effective potential for a Schwarzschild black hole. Are you taking that into account, or are you also taking the effective potential for Kerr black hole as well?
Yeah, I mean, in the sense of we do in the Newtonian. So in another paper with Yannick and others, we actually worried about that. So this will come as a spin orbit interaction contribution to that effective potential.
Okay. The question I have is that if once you see actual observation of the wave and so on, how would you know that your calculations are not deviating from pure GR and some sort of a modified gravity or whatever? I mean, some corrections to GR is, I mean, there will be some mismatch with your calculations as with the LIGO, waveform.
Okay.
How would you be sure that it is just observational problem, or there is something, something significant there?
Okay.
From so the waveform you have calculated.
Sure, I know. So if you look at the observational aspects, there is a 10% problem in the calibration for the time being. It will get better and better down the line. But if you look at the gravitational waveform, so there are efforts where, for example, from Johnny Lee, Arun, and many others. So they will actually parameterize the deviation from GR, and then you try to constrain those parameters. So in a phenomenological manner, so that you will not say that, I'm interested. So for example, if there are going to be dipole radiation, that can be constrained from gravitational wave observation, but I will not care whether it's a branch decay or there's a hair on the black hole and things like that. So there is, and also, so every Newtonian order in this template, there are, terms put in by hand, and you actually constrain. So your quadrupolar correction, deviation from the quadrupolar contributions, they can be, for example, compared with the pulsar timing array. After that, there are no pulsar timing array, pulsar timing constraints. So these higher order contribution to the frequency evolution are being constrained by gravitational wave observation. Am I clear what I'm trying to say?
Yeah.
Okay. So you don't need to worry about a specific theory. Of course, you can use those inputs and create a theory by yourself, or take some. and then say that in your theory, what is expected and whether it's consistent with LIGO.
Okay.
Okay, any other question? I don't see any raised hands, so we thank you, Gopu, for your
Thank you.
talk.
I will, yeah, I already
Yeah,
stopped
so
sharing, right? Yeah.
then our next speaker is Indranil, and he'll be talking about particle production in accretion disks around Indranil.
Yeah. I have shared my screen. Is it
But
visible?
not in full screen mode.
Yeah, fine. But it's visible, right? Okay.
Yeah.
What's wrong? Just a minute. Something's wrong. Yeah. Yeah. All right. So from time-dependent space-time to stationary space-time. So I will be talking about stationary black holes in the sense that its space-time is not changing in time. The kind of black holes we see in mostly in AGNs and microquasars. So I'll be talking about particle production. Okay, all right. So accretion is the best model to explain luminosity, spectra, timing properties from AGNs and microquasars. And also it has been observed that a amount of matter that leaves those objects. So there's some jets and outflows are observed. So therefore, since black holes will not be ejecting matter, so it is quite normal to assume that the fraction of matter are redirected as bipolar jets. The first part, I'll be sort of giving an introduction of accretion and ejection system. So it has also been observationally established that the jet states, you don't see jets all the time. The jet states are correlated with accretion states, especially in microquasars. And since microquasars have short dynamical time scale, therefore it changes states faster, while AGNs will take much longer time because it's heavier. The dynamical time scale is much larger. So if you canonically one sees a black hole candidate in this hard spectral state. It's from Cygnus X1. I've forgot to give the credit. It's from one of Putin's paper. I don't remember from where. So what is essential is that we have in this hard state multiple power laws. So you can see a power law here and a power law there. And then it is also, sometimes it is there, sometimes in other objects not there. There is a multicolored black body. Multicolored black body is summation of many black bodies with different temperatures. Okay, so it's supposed to come from Keplerian disk. All right. So also there is another accretion state which is called the soft state. So which is marked by the power being, maximizing at softer part of the spectrum, and again is the dominant multicolored black body, and then there is a long power law here. Okay, so that's called the soft state. This is an intensity hardness diagram. This hardness ratio on the x-axis and the intensity on the y-axis, which shows how the various microquasars change states. So the soft states are here, the hard states are there. These are the intermediate states when it transits from hard to soft. And the jet states, and here the jets are sort of in a cartoon diagram. And one can see the jets are found in the low hard intermediate states. And during the transition from hard to soft, there is a relativistic ejection. And then in the soft state, there is no jet. Okay. So these are all, overall, very broad observational features. So there is also enough indirect evidence that the large-scale jets are matter-dominated. Okay, so Jets are also appeared to be launched from a region very close to the central black hole. This is Juno Beretta Livio old paper, and this is taken from, this is a stacking of radio data from M87 again. For 20 years, data has been stacked to make a movie, and you can see that the matter is coming out here, okay, with almost the speed of light. Now, accretion onto black holes is trans-relativistic in nature. That is, at large distance, the flow is non-relativistic, but close to the horizon, the flow is relativistic. And it is relativistic in terms of both kinetic term as well as the thermal term. At far away, it is slower and colder, and close to the horizon, it is faster and relativistic and hotter. Jets, on the other hand, are just the opposite. So close, not the opposite, I mean, it's quite different. So close to the horizon where it is being launched, the velocities are fairly subrelativistic, but it's very hot. Further away, where the jets achieve relativistic speeds, the temperatures are much lower. So the important point to note, the jets are launched from accretion disks, and that the matter is quite hot there. So, but further out, it will be non-relativistic. So therefore, the plasma around the compact object are fully ionized and thermally relativistic. Okay. So in general, when we try to study these objects, the general method is to use relativistic equations of motion, but then use equation of state to describe the thermodynamics of the gas, which is basically a Newtonian based on Newtonian kinetic theory. Okay. A consistent relativistic equation of state can be computed and has been computed by Chandrasekhar a long time back. So you take, instead of considering the energy to be non-relativistic, you consider the energy of particles to be relativistic, and then you again assume it to have a Maxwell-Boltzmann distribution. Then if you integrate the energy of the gas, and which is basically a combination of modified Bessel's function and function of temperature. So the problem with, but it has never been very popular, and the reason being, it's because it's combinations of a modified Bessel's function. It is difficult to use, and it has been done. It's not that it has not been done, but the problem is it can break down at low temperatures and high temperatures in a computer code. And to implement them in numerical simulation codes, it makes the codes very, very expensive, in the sense computationally expensive. So there have been many efforts to mimic the relativistically perfect equation of state, which is acronymed as RP. We had done that some time back, and we fitted with an algebraic temperature as well as composition, and we called it CR equation of state from the authors of the, it is basically abbreviated from the author's names. And so it is basically the energy density is the rest mass energy of the electrons, and then you have an F, which is essentially a function of temperature. It's a non-dimensional function of temperature, where theta is basically a temperature, n is the polytropic index, and gamma is the adiabatic index. One can see that they depend on the temperature here. But to be fair, we actually don't need this polytropic or adiabatic indices at all, because everything is function of temperature. But to sort of satisfy ourselves, we plot here the adiabatic index with temperature, and we can see at low temperatures it is approaching gamma 5/3. At high temperature it is approaching gamma 4/3. But not only that, it also depends on the kind of gas we have. If it is an electron-positron gas, then it achieves gamma 4/3 close to 10 to the power 11 degree Kelvin. while if it's an electron proton, xi is the ratio of proton number density with the electron number density. So this should be, the upper curve should be the electron proton, the lower will be electron positron. And we have also compared with the Chandrasekhar equation state or RP equation of state. The lower curve, which is snuggling these two curves, say for xi equals to 1, the lower one is our proposed, while the upper one is actually calculated RP. You can see it is almost the same. Okay, maximum deviation is less than 0.06% or something, less than 0.6%, less than 1% in fact. So now to introduction on various disk models. Now, if the first accretion model was the Bondi model, which had a gravitating center here, stationary metric, and radially matter falling in. So it was solved by Bondi, and then it was in Newtonian domain, but then it was repeated in GR by Mitchell in 1970 something. And but it lost favor because the matter is falling radially, it's falling too fast. It cannot produce the luminosities we tend to see. The next one was the Keplerian accretion disk, proposed by Sakura and Sunyaev in the Newtonian version, then the GR version in the same year by Novikov and Thorne. And this is the in the movie Interstellar. This is the accretion disk that was shown on around Gargantuan is the Keplerian disk. Okay, so if that is of any interest. So so basically now you get rid of all the advection term, and you also get rid of the pressure gradient term along the radial direction, and you balance, you get a Keplerian angular momentum distribution. And then you assume that there is also viscosity, and then viscosity transfers angular momentum outward, and then matter falls in a very slow manner. So that's a Keplerian accretion disk. Luminosity is very high, but the power law emission cannot be produced with the Keplerian disk. Then there was thick disk, which was very promising, which could produce the power law emission. However, it turned out to be unstable. Again, in the thick disk, what it was done was the pressure gradient term was kept, but the advection term was not kept. So without the advection term, it became unstable. If you plug in that advection term, it becomes stable. So what we do is we solve everything, all the terms and so on. If it is a simulation, then we can go for three-dimensional without any assumption of axisymmetry. But if it is analytical, we have to restrict to axisymmetric solutions. So this is the generality mu nu, and so on and so forth. Okay. So the Euler relativistic Navier-Stokes or Euler equation is given by this. The first law of thermodynamics is given by this. You can integrate them, and you can get the constant of motion, which is generalized Bernoulli parameter, which is for Kerr parameter something like this. In absence of dissipation, this will just be minus HU sub t. Anyway, how to solve it? Because this viscosity, angular momentum is not known. So what we have to do is to iterate the solution. So everything is known on the horizon. However, horizon also have a coordinate singularity. We actually cannot integrate from it. So what we do, we go asymptotically close. We get this get the asymptotic values by some Frobenius method and on from the horizon values and so on, and then we sort of iterate. Okay, so this is one solution go like this, the other solution will go up above, and slowly you can sort of settle down into a solution that passes through critical points. Okay. All right, so if you do that, we get, this is the energy, this is a generalized Bernoulli parameter, and this is the L naught. L naught is the angular momentum on the horizon. And if you plot them, you have to see all kinds of solutions. So these black arrows are the accretion solutions. Okay, so this is for alpha, the viscosity parameter of 0.01, and for electron proton flow, xi equals to 1. Okay, here there's a curved solution with on the right hand side we have plot the Mach number. The red one is for the accretion, and the blue ones for the jets. And you can see that, here is the cross section of the flow. The red one is again for the accretion, and the blue one is for the jet. And what it does, the curve parameter, what it does, it twists the space-time around it so much that it also creates a shock in the jet. Okay. All right. So I'm not going to details of that. So so far we did not consider, these are all a little bit dated papers. So far we did not consider the particle production or annihilation. Okay. So the important thing to ponder is the temperature close to black hole can be few tenths of MeV, which is, I mean, which should sort of encourage particle production. And a lot of high energy radiation may be produced. So in this talk, I will just restrict myself to pair production and annihilation. All right. So you can see here that you can have very high energy radiation that is coming up. So the possibility of pair production is pretty high. All right. So in the pair production, you can have the various processes like photon-photon interaction can give rise to pairs, photon-particle interactions can give rise to pairs, and particle-particle as well can give rise to pairs. So that's sort of codified here. However, the reaction cross sections grows like one by one in the ratios of alphas, the fine structure constants. So one can see these are not very dominant. Okay, the more dominant pair production part is the photon-photon. All right. So we sort of get rid of all those. We can put a little bit on this, but for the first effort, we sort of got rid of all of them. So then, but once we create pairs, it will affect the luminosity, of course, but it also will increase the optical depth. Okay, so therefore, the spectra will also be seriously affected. And so what we have considered is the radiations from bremsstrahlung and the Comptonized bremsstrahlung. We have at the moment not considered synchrotron just because it takes a little bit more time to do it. Okay, so now if you could compute pair production, then one is left with an additional positron term. Okay. So the changes in the equations of motion is the proton is conserved, the proton number is conserved, so we can sort of integrate that. So we have a proton accretion rate, but positrons, because I mean being created and annihilated, are not conserved, as well as the electron numbers are not conserved at all. So now the radial momentum equation, we use the same radial momentum equation, but in there we have this pair terms, creation and annihilation terms, apart from viscosity and other heating cooling terms. So we can write, this is a three radial velocity. We can sort of rewrite the equations in this form where it goes like n by d, where p's and are the the amount of energy that has been internal energy consumed to produce pairs. Then we have the azimuthal component of the flow, where L is basically use of phi. So the covariant component of the azimuthal velocity, okay, for velocity. All right, and then the first law of thermodynamics can be sort of simplified into this. So now we solve these three equations: dV dr, dl dr, d theta dr. Previously, we also were doing that, except that we didn't have these terms, these q's and these p's. All right, and if you integrate again, we can find out again something constant of motion, which is again the Bernoulli parameter. So we use that to find our solutions. Now, what we do first is to find a transonic solution without pairs. So we take a electron-proton flow. You can see here that in the middle panel that xi is equals to 1, which is number of electrons is equals to number of protons. And then we find the solution first. And once we get the temperature distribution and we calculate the photons, from those photons, using the pair production terms, we calculate a posterior proton distribution. And once we do that, then we also calculate the annihilation terms, and then we plug on those in the equations again and again recalculate, okay, in the second iteration. So now you see some amount of protons have been created. The xi, you see, is dipping, okay? And there is a change in this is the Mach number, which is the velocity by the sound speed. There's a change in the Mach number here, although it's not perceptible there. Okay, so now once there is an annihilation term, you can see there is this bump, annihilation bump here. Okay, then again the third, so we can take that, we again recalculate, and then we get the third iteration and so on. So after 6-7 iterations, generally the solutions converge, and once it is converged, we have a solution. Okay, so here what we have plotted is a solution around a Schwarzschild black hole with the Bernoulli parameter 1.001 with the angular momentum. This is very close to the angular momentum on the horizon, specific angular momentum, and with the viscous parameter 0.01 and on 10 solar mass black hole with accretion rates 0.1, 0.4, and 0.8. Here you can see the ones with 0.1 and say 4, they almost merge. Okay, there's not much we can see, and you can see the change in xi is very, very low. But as we increase the accretion rate to 0.8, we can see the solution changes, the Mach number change, the distribution of angular momentum changes, as well as we can see there's a lot of a lot of pairs are being created. So xi gets a dip. Okay, and while for 0.1 and 0.4 there is not much change in the spectra, there is, but there's no signature. If you just look at the spectra, you will not be able to say this is in production of, there is some pair production or not. But for 0.8, we can see there is a spike. Okay, so there's an annihilation line spike, 511 kV, slightly deviated from the 511 kV mark because of gravitational and special relativistic, smearing of the frequency lines. So now we focus on the 0.8, but of course for different angular momentum and viscosity parameter, but the same accretion rate and same Bernoulli parameter, 10 solar mass again. What we can see here, what we have plotted here is a spectra from various regions of the accretion disk. So, for example, this one is from between two from the horizon to the 1.5 photon orbit. Okay, and this is the spectra what you can see here. Okay, right, and then between 3 and 5 is the blue one. So if you look at the total spectra, this is the blue spectra. Okay, and then between
5 minutes.
Yeah, just I'm almost through. Again, the green one is between 5 and 8. You can see again the green one and so on. But beyond 100 Schwarzschild radius, we don't see any signature. There's no significant pair production at all. Okay, so that's what we can see from here. So I'm almost through. I'm through basically. So let's. One of the point I would like to add here is that because jets. So if you study particle production, it can also contaminate the matter away from the source, the microquasar or AGN. Thank you very much.
Thanks a lot, Indranil. I have Ritaban who wants to ask a question.
Yes.
Hi, can you hear me?
Yes, sure.
Yeah, so there is a sort of belief that pair production will sort of slow down the jet. So can you see that in, is your machinery in that sort of?
We haven't studied the pairs, effect of pairs in jets. Okay. Not in this. Actually, pair producing production of pairs in the jet. We haven't studied. We have studied jets which have a lot of pairs and then do all sorts of things. That is there. Okay. But the effect of pairs within the jet we have not studied. But of course, we like to study that. One can say that if you are producing pairs, so you have to. From where you're getting the energy from? It is from the jets itself. Right, so if the jet itself is producing pairs, a part of the internal energy will be eaten up. So
Right.
it might slow down. But on the other hand, if the pairs are produced mostly from the accretion disk photons, say inside the jet, okay, then it might have a different effect altogether, because there's an external energy input. I mean, did I make myself clear? No.
Yes, yes.
Okay.
Any other question? Please raise a hand. Shantanu, go ahead.
So this is mainly a pedagogic question and probably very basic. So I just want to ask for the Chandrasekhar equation. So what kind of fluid it describes, and is there a physical reason why it is not used apart from the fact that what you mentioned is difficult
there's
to
no
compute?
physical reason. There's only that it was difficult to implement. People have used it, but it's very difficult to carry on these this Bessel's function, modified Bessel's
What kind of, can you just put up the equation of state, and I mean, is it close to the Zeldovich equation of state, which describes a very stiff fluid? I'm just trying to understand the physical.
Okay, so if you look at it doesn't describe just a stiff fluid. It is a transrelativistic fluid. So if you look at here, so I mean, our equation state and this RP, or the Chandrasekhar equation of state, you can see it sort of snuggles together. So you can just take it there. So it goes from 5/3 to 4/3. Okay, it just flows there. Okay, so as such, physically there is no problem at all. People have also tried, because nowadays the analytical investigations are over almost, you can say. I mean, it's people do analytical things to understand the physics, but if you have to really predict and do serious science, you have to do the simulations, and in simulations, installing that itself slows down a very simple special relativistic code by a factor of 50%. It will just eat up. It will be just 1.5 times. Now, if you implement various physical processes like radiative processes, or some heating processes, some pair production, or some particle annihilation production processes, that will slow down the code like hell. And if you add now magnetic field, it will be very difficult to control those and do some meaningful science. So there has been many effort amongst the numerical simulation people to propose something. Okay, so the more general people use is what is called the TM. So in 1948, Taub wrote a paper on relativistic, I mean the relativistic Rankine-Hugoniot conditions. But there he did not assume any equation of state. But there, from applying Schwartz inequality on the equations of motion, he derived a fundamental inequality that all relativistic gas must follow. Okay, so that the lower limit of that inequality has been used by many people, which is much simpler. But again, it becomes difficult to justify. It can just go up, I mean, become hotter where it should not be, and colder where it should not be. In fact, I mean, we wrote a paper with one of my students last year, I think, yeah, on relativistic MHD, and we used this equation of state, and there were cases, and we compared with the fixed gamma equation of state, that with the equation of state where the gamma is constant, and we found that the ones which we are using with gamma 5/3 was hotter than the ones which are using gamma 4/3, which should be the other way around. Okay, so the fixed gamma actually messes up a relativistic flow in a non trivial way. It's better to use these.
Okay, I don't see any other raised hands. So thanks a lot, Indranil, for giving us this interesting talk. And next speaker is Bhaskar Biswas. Are you there? Yeah, Bhaskar, can you upload your slides? And he'll be talking to us about the properties of the secondary component of the binary GW190814. And here.
Thank you, Harvinder. I hope I am audible, right? And you can see
Yes,
my screen.
yes. I will.
Thanks. So I'll start. So at first, I would like to thank the organizers for giving me this opportunity to present my research work here. So the title of this talk is GW 190814 on the properties of secondary component of the binary. So this talk will be based on these two archive papers, which are linked here. So at first, I would like to start by briefly introducing the interiors of a neutron star. So one of the key challenges of current astrophysics is to constrain the equation of state of neutron star. So as you know that neutron star has mass of the order of mass of the sun, and its radius is of the order of 10 to 15 kilometers. So you can imagine how dense that material could be. So at the center of a neutron star, the density could reach up to 10 to the power 15 gram per centimeter cube. But the temperature of a neutron star is very low. It is of the order of 10 to the power 7 Kelvin. So when I say low, it is that means it is lower than much lower than the Fermi energy of the neutrons and protons inside a neutron star. So if we see this plot here in this x-axis, the temperature is plotted as a function in the scale of MeV, and in the in the y-axis it is, and in the x-axis the net baryon density is plotted. So now, in normal lab experience, the materials which we deal with, they mostly lie in this region, where the temperature and also the net baryon density is much lower. So now, in order to go to the high density, we have built a particle accelerator. So, for example, the LSC, if you go to the high temperature around 100 MeV, we can probe this region. But neutron star, they lie in this region, which is roughly order of 10 times much higher than the normal nuclear density, and also its temperature is much lower than those particle accelerators. So therefore, it is clear that we cannot make neutron star like material in our lab, or in either in our lab or in our particle accelerator. So therefore, only way we can probe neutron star equation of state through the astrophysical observations. Now, neutron stars are observed in different bands. So recently, it has been observed in gravitational waves. Also, it is observed via X-ray and radio also. So in this paper, what we have done, we have combined all those observations to put a joint constraint on the neutron star equation of state. So here in this equation, the thetas are the equation of state parameters in some equation of state models, and D is the data, and this is the posterior of the equation of state parameters given a data, and this is the Bayes theorem which we use to constrain the equation of state parameters, and here it is a combined likelihood. So DI stands for each kind of data here, and P theta is the priors on the equation of state parameters. So that will be determined by our nuclear physics knowledge or some lab experiment results. So in our calculation, we use two GW observations, that is GW 170817 and GW 190428. So those are the two BNS observations, and one X-ray observation, which is made by NICER collaboration. So they, for the first time, they have provided very accurate measurement of mass and radius of a neutron star, and also a heavy mass pulsar observation, from which we get very accurate information of the neutron star mass. Now, in order to estimate this equation of state parameter, we need to assume a model for equation of state. So one of the most commonly used model is piecewise polytrope model. So in this model, actually, one divide the neutron star interior in different pieces, and for the different pieces, they use different polytropes. So that the polytropic equation of state. But these models are not directly indicative to the nuclear physics. So what we have done that we know there is some information we come from the nuclear physics lab, which experiment near the saturation density. So near the nuclear saturation density, the energy per baryon can be divided in two terms. One for the symmetric nuclear pattern, that is E naught rho. So for this part, the number of neutrons is equal to the number of protons, and another for the asymmetric nuclear pattern. So this is the eSym. So this is also known as symmetry energy. So this tells us how symmetric or asymmetric the matter could be. Now we can go a little bit further, and we can expand these terms in Taylor series and around the nuclear saturation density, that is rho naught, and we get few parameters. So these are the parameters which are shown in this magenta color. So our target is to constrain those parameters from the data, and these parameters are used up to this 1.25 N naught saturation density, because after that this may become invalid, so you cannot use it further. And at high densities, we do not know about the neutron star equation of state. So at that high density, we use some phenomenological equation of state like piecewise spectrum. So based on this equation of state, we constrain the equation of state of neutron star by combining all the astrophysical observations. So I would like to focus your attention to this particular panel. So in this panel, the present constraint on the neutron star equation of state is shown by this shaded diagram in the mass radius panel. So this is the now present constraint of the neutron star equation of state based on the equation of state model we have built. So in this talk, I'll be focusing on this particular observations, which is named as GW190814. This is probably the most enigmatic observation which LIGO has made so far, because this observation is associated with a mass, with a compact object which has mass around 2.6 solar mass. So this particular object lies in a region which is firmly placed in the mass gap. So we do not know whether this object is a black hole or neutron star. So also we haven't observed any electromagnetic follow-up associated with these observations. So what we have only the mass estimate of this observation of this object. So it is plotted here in this blue color, and in the orange color, the maximum mass distribution of a non-rotating neutron star is plotted. That we have obtained using our previous study, where we combined all the astrophysical observation to constrain the equation of state of neutron star. And based on this distribution, we have computed what is the probability that this particular object is associated with neutron star. We find it is roughly order of 1%. So, but here we do not take another possibility that neutron star could be rapidly rotating also, and rapid rotation can increase the mass of the neutron star up to 20%. So, if we consider rapidly rotating neutron star scenario, then this mass estimate could be satisfied properly. So in this paper, we have taken different assumptions. One is a non-rotating neutron star hypothesis, and there is rapidly rotating neutron star hypothesis. And based of these assumptions, we have calculated what could be the properties of that particular compact object. So I'll first talk about the properties, assuming the neutrons that compact object is a slowly rotating neutron star. Here I'll focus your attention to this particular plot, which is the rightmost plot here. In the y-axis, the pressure inside the neutron star is shown, and in the x-axis, the energy density is shown here. And in this plot, in the black dotted line, the priors on the equation of state are denoted here, and the blue shaded region, the equation of state posterior is shown after adding this GW190814 observations. So you can see that after adding this observation, we are getting a very stringent constraint on the equation of state of the neutron star, and it is very steep. It is telling us the equation of state will be very steep, because now very few equation of state now can actually accommodate that amount of high maximum mass of a neutron star. Now I'll go to the rapidly rotating neutron star scenario. So in this paper, for the first time, we have built this one Bayesian inference technique to constrain the properties of a rapidly rotating neutron star from GW observations. But I'll not go to the details of this method. I'll directly go to the results. So here we are showing the properties of this object, of this compact object, assuming it is rapidly rotating. So let's focus to this plot. Here, the posterior distribution of the rotational frequency of this object is plotted. And you can see the median value of that frequency, it comes around 1100 Hertz. So therefore, till now, the maximum spin of a pulsar is known to be 716 Hertz. So if this object is indeed a rapidly rotating neutron star, so this will be this could be the fastest rotating neutron star observed ever. However, any rotating neutron star is actually generically unstable through a mechanism called Chandrasekhar-Friedman-Schutz instability. So this mechanism tells us that whenever a certain mode, which is retrograde in a rotating frame, if it becomes prograde in the inertial frame, then that mode becomes unstable. And it is true for R mode or rotational mode at any values of frequency. However, there are inside a neutron star, there are certain physical mechanisms like viscosity, which also depends on the neutron star temperature. They can damp this that instability. And depending on the temperature, there is an instability window, which is shown here by that line. So in this x-axis here, the temperature of the neutron star is plotted, and in the y-axis, the rotation rate is plotted here. So now you can imagine, let's say a newly born neutron star, which has a very high temperature and also somehow it gets some high spin. And after the time, so it is lying around here. After some time, when the neutron star cools down, it comes inside that instability window, and the R mode becomes unstable. So as a result, the neutron star will spin down and it will follow this line, and after some time, it will end up here. So with any old neutron star which has very low temperature, we do not expect them to have to retain that kind of high spin. And in a binary system, we expect the neutron star will be old. So it is very unlikely that, that such a neutron star will possess that kind of high spin. So therefore, in this paper, we have considered the both hypotheses. One is non-rotating hypothesis, another is a rapidly rotating hypothesis neutron star. And we found that both can satisfy the observed mass. However, the condition we need, that is bit extreme.
Bhaskar,
So,
you have minutes?
yeah, I'll be finishing this. So that makes the object more likely to be a black hole. And if that object is a black hole, it can also tell about tell a lot about the neutron star equation state. Because if we now assume that the population distribution of neutron star and black hole, if they do not overlap with each other, then this object will place an upper bound on the neutron star maximum mass. And taking that upper bound, we have run our Bayesian analysis again, and we have constrained the equation of state of the neutron star. And those equation of state are now used to plot this maximum mass distribution. And we found that at 90% confidence interval, the maximum mass is now around 2.22 plus minus 0.2 solar mass. So this is the most stringent constraint on the maximum mass we are getting so far in the studies. So in a summary, we have developed a hybrid equation of state formulation which connects the equation of state the nucleophysics information at a lower density and with a generic parameterization at the higher density. And we have also shown that no-fail constraint on the neutron star equation of state could be obtained by combining multiple observations. And later we focus our attention to this particular observation GW 190814, which harbors a mass gap event. And we have found there is only 1% probability that this object could be a non-rotating neutron star. And if it is true, that would imply very steep equation of state for the neutron star equation of state. And for the rapidly rotating hypothesis, it qualifies as the fastest rotating neutron star observed ever. However, we have argued that in order to be true, in order to be both cases to be true, the condition we need is very extreme. So that's why this object is more likely to be a black hole, and the methodology we have built in this two paper that can be used to take into account any upcoming astrophysical observation of neutron star to place further constraint on the neutron star equation of state. So thank you very much. If I would be happy to take questions now.
Thanks a lot, Bhaskar. I have one raised hand over here. Ranjan, please go ahead.
Hi. In your last slide, previous to the summary, you showed the population density function. It goes up to 3 at 2.2, around 2.2 solar mass. What does that mean? I mean, what does it signify?
It goes up to 2.3. Sorry, I
no. Yeah, the population density function goes to 3, around 2.2 solar mass, right?
No, this is the PDF. This is the probability distribution function.
Okay, probability distribution function. So it should go up to 1, right? It is going up to 3.
No, it has to be normalized here. So maybe it is not normalized right now. I have to check it.
Okay, thanks.
Okay, next question is from Indranil. Please go ahead.
Hello, Bhaskar.
Hi.
Hi. So I have a query. So generally speaking, neutron stars are taken slightly over 1 solar mass, the mass, and the radius is around 10 kilometers. Now, if you actually go beyond 2 solar mass, so then the equation of state will dictate what should be the radius, right? So if you are actually going up in mass, so I mean, what is your best take that which equation of state will sort of predict an acceptable radius.
So if you
Did you
go
get
to,
my question?
yeah, so if you go to the higher mass, that would imply you need a very steep equation of state in order to accommodate that amount of higher mass. And if you go to the steeper side, then the radius will also be high. So if you see this plot here, right now this is this panel particularly, and this is the present constraint on the neutron star equation of state in the mass radius curve. So the steepest equation of state which I am getting here has around radius around 13 point some kilometer. So that is right now the present constraint we're getting.
All right. Thank you.
Yeah, thanks.
Thank you, Bhaskar. And our last speaker of this session is Nirban. Nirban, are you there? Please. Nirban Bose. And we'll be talking about model independent constraints on binary black hole systems. Nirban, please share your slides.
Are you able to see my slides?
Yes. Yes.
Okay, thank you. Yeah, so thanks a lot to the organizers for giving me an opportunity to present. Hello, everyone. I hope I'm audible and my slides are visible to all. So today I'm going to talk about a phenomenological model-independent approach to constrain eccentricity of binary black hole systems. This work is done in collaboration with my supervisor, Archana Pai. So moving on. So compact binary systems with black holes and neutron stars are primary sources of interferometric gravitational wave detectors like LIGO, Virgo, and Kagra. But majority of these black holes, by the time the signals from these black holes enter the current sensitive band of the ground-based detectors, they're believed to be circularized. But there might be cases, and in fact, recent studies suggest that with increasing sensitivity of the interferometric gravitational wave detectors, there might be black holes who retain a significant higher eccentricity by the time they enter the sensitive band of the LIGO and Virgo detectors. Now, these systems are eccentric systems, and they are interesting because of the fact that they are generally formed in dense stellar environments like globular clusters or galactic nuclei. Now, in these dense systems, what happens is dynamical encounters between the black holes are very common. So as a result, what happens is these binaries don't get time to circularize by the time they enter the LIGO band. So they retain significantly high eccentricity in the observational band. So it's very important to study about these eccentric systems, because studying about the eccentricity of these systems will help us probe the formation channel of these systems. But one important question in this regard is that in order to study about the eccentricity, we need to have an accurate measurement of eccentricity of the systems. But currently, as far as the templated searches are concerned, there are no extensive template-based model searches for EBBH systems, because because of eccentricity, there is an additional parameter, and the dimensionality of the parameter spaces are increased, and hence the waveform modeling becomes difficult. So there are few available waveforms like eccentric TT, eccentric FD, SOBinary, a number of NR waveforms, but each of them have their own limitation in terms of eccentricity range or spins and all that. Study of complete IMR in-spiral merger ring down, including spins and high E waveforms, are under development, as we also saw from Gopu's talk. So complete parameter estimation as of now is limited by the availability of waveforms. And even if we have a good number of waveforms, there might be cases, as has happened in the past also, some models, so the analysis becomes highly model dependent, in the sense that some models might predict something, some other models might predict something, and they might be inconsistent with each other. And the base factor might be not strong enough to comment anything. So we need to have robust model independent methodologies to constrain the eccentricity. So with this motivation, we move forward. Just to briefly sum up the orbital dynamics from the spiral phase of the BBH systems, they are well calculated by the Peters and Matthews equation. And if you consider a two-body system separated by a semi-major axis of A, and they come closer to each other, the orbits shrink by emission of gravitational wave radiation, and all these physical quantities, the semi-major axis, the energy, the eccentricity, the frequency, the rate of change of these quantities is heavily dependent on eccentricity. and the equations are highly nonlinear and coupled. So it's not possible to solve them manually. So we restore to numerical methods. What we do is we evolve the eccentricity, time variation of eccentricity. We evolve the eccentricity as a function of time and use that eccentricity information to df/dt expression and calculate the frequency evolution as a function of time for these eccentric systems. And if we plot different frequency evolution with respect to time for different eccentricities, we see that for higher and higher eccentricities, the duration of the signal decreases. This is intuitively obvious in the sense that for any eccentric system, there is a degree of asymmetry associated with the system, and higher is the eccentricity, so more the system will try to throw away the asymmetry and try to circularize itself by radiating more and more gravitational waves, and it will merge quickly. So higher is the eccentricity, shorter will be the signal. Now, in case of circular system, in the df/dt expression is well characterized by the chirp mass parameter, which is a certain combination of the component masses. And from the slope of the log of frequency and time, we can get this chirp mass quantity. And similarly, in eccentric systems also, the df/dt expression can be the slope of the log f and t can give us a similar quantity, which is this curly me parameter, which is not strictly the chirp mass of the eccentric system. It's a scale slope, but roughly it can be referred as an eccentric chirp mass. So different eccentricities will give us different time frequency evolution, and hence in the slope of the log of frequency and time, this information of eccentricity will be captured. Just to quote in terms of numbers, for the first event, GW 150914 event, it had a chirp mass of around 28.19. If we take the same event and evaluate the different eccentricities, 0.2, 0.2, 0.3, 0.4, it gives us curly M parameters of 29, 30, and 34. So like as I mentioned, that higher the eccentricity, the time frequency evolution will be different. For higher eccentricities will go on shorter, that will give rise to steeper slope, and hence that will be reflected in ME. So we are getting a direct correlation between ME and E, which we try to model. So in order to do that, we consider stellar mass black hole systems in the eccentricity range up to 0.6. We numerically evolve the frequency and time of these systems. And from the slope of F and T, we try to evaluate the ME parameters, which we try to fit in terms of a polynomial of E square, and obtain the ME as a function of the chirp mass and E, where the coefficients of the polynomial are functions of the chirp mass itself. So here, point to be noted is that we have three quantities: the curly ME, which is roughly the eccentric chirp mass, the ME, which is the M, which is the circular chirp mass, and E, which is the eccentricity. Now, suppose if nature gives us a system and we detect it, we priori don't know what will these values be. So we need to estimate the parameters. But the thing is, if we try to estimate the chirp mass of an eccentric system with a circular waveform, obviously the results will be biased. But the question is there? But the question is there? Sorry. Yeah. But the question is there any systematicity in the bias? And can we comment anything from that systematicity, and has it got something to do with the eccentricity and the chirp mass? So in order to study that, we run an injection campaign. We inject equal mass non-spinning EBBH signals using eccentric TD waveform in simulated Gaussian noise colored by A plus PhD. The injections span a chirp mass space of 8 to 30 solar mass and an eccentricity space of 0.1 to 0.5, and all of them have a good amount of optimal and spiral SNRs in the range 35 to 65. We estimate the chirp masses using a non-eccentric IMR phenom PV2 waveform using the Bilby package. This is sample posterior. And for those same systems, same set of systems, from the fit, we try to evaluate this eccentric chirp mass, and we find that for low to moderate eccentricities of up to around 0.3, they agree pretty well, while the linearity deviates for higher eccentricities. So this is intuitively obvious, because for higher eccentricities, since it will try to merge quickly, we'll have less number of spiral cycles and hence less SNR. Now, the thing to be noted is for y-axis, we have the measurement from PE, and in the x-axis, we have measurement from the fit, which is in turn measured from the time frequency, from the slope of the frequency and time in the time frequency map. So And the next thing is to go to the time frequency representation. And if we go to the time frequency representation, a lot of interesting stories actually pop up. So unlike the circular case where we have a single time frequency track, in case of eccentric systems, we'll have these multiple tracks which corresponds to the different modes, eccentric modes. And the frequency evolution of these different modes actually is related to the quadrupolar or the 2-2 mode by a scaling relation of m by 2, where m is an integer. And the power in the different higher order modes is actually well calculated by the Peters and Matthews, which is again a function of eccentricity. So the important thing is there for low to moderate eccentricities, the quadrupolar mode is dominant, whereas if you go to higher and higher eccentricities, the other higher order modes start to kick in. But in order to estimate the chirp mass, we will use the dominant mode, 2-2 mode, which can be fitted using the numerical evolution. Now, in order to validate our recipe, what I have been talking about, what we do is inject an equal mass non-spinning EBBH signal with component masses 2020 and chirp, which corresponds to chirp mass of 17.23, eccentricity 0.3, with an optimal SNR of around 45 using eccentric TD waveform in simulated Gaussian noise colored by A plus PSD. So if you do a parameter estimation using AMR phenom PV2 that estimates curly ME parameter of 17.83, while from the slope, and that is estimated to be 18.9. And if you use a reference curve, which we obtained earlier, we find that our point lies in the chirp mass space of 15 to 20 solar mass and an eccentricity space of 0.3 to 0.33. Now, the good thing is that without using any prior information about the waveform models or the mass values, we are able to constrain the chirp mass and eccentricity within this grid. Now, we want to further narrow down this grid. In order to do that, we develop a consistency test using the higher order modes. Now, the thing is, what we do is using the constraint obtained from in the previous slide, the chirp mass and the eccentricity grid, we pick up points within that grid and we simulate that numerically simulate the time frequency tracks and try to fit them in the time frequency track of the real data. Now, the best fitted track will be that track whose energy will be maximum. Now, we find that among all the systems within this constrained range, the energy is maximum for the 17 and 17 chirp mass and 0.3 eccentricity. Now, the next question arises is, if that is the best fit system, then obviously, if we use the scaling relations and try to find the energy along the other tracks, other higher order mode tracks, we'll notice some other peaks in the energy curve. And indeed, if you vary the m by 2, yeah.
2 minutes.
Yeah, fine. And indeed, if you vary the m by 2 values of the tracks and try to fit them, we find that the maximum energy is at m by 2 equal to 1. Apart from that, we get two other bumps in the energy curve at m by 2 values of 1.5 and 2, which corresponds to the 3.3 and 4.4 modes, which clearly depicts the presence of the other higher order modes. So this indicates that with no prior knowledge of any models or our mass values, we are able to constrain the chirp mass and eccentricity to a sufficiently good extent, and as well as detect the presence of the higher order modes. To conclude, we devised a model-independent phenomenological approach to constrain eccentricity of binary black hole systems in the advanced ground-based gravitational wave detector regime. We used the chirp mass estimate from the time frequency map, as well as the systematic bias the eccentric nature of the event and further narrow down the range of the values. We develop a consistency test using the higher order modes. So our heuristic approach has direct application in the model independent eccentricity estimation for generic stellar mass eccentric systems in the upcoming observational runs. And the current draft is under preparation, which we plan to freeze soon. Thank you.
Thank you, Nirban. Any question? Gopu, please go ahead.
Very nice talk, Nirban. So when you showed that the time domain higher harmonic expression, right, in terms of the Bessel function, I vaguely remember that. Yes, is this the one? Yes.
Yeah.
Okay, so see, the problem is that those higher modes, they are going to be shifted because of the periastron advance, and that may have you incorporated. It was very quick, I didn't quite see it. So the position of those higher modes are going to depend on the rate of Fourier-Tron advance, and that cannot be written in terms of the chirp mass. The mass ratio will come into the picture. So have you thought about those?
Yeah, thanks Goku for the input. Yeah, so currently what we have tested in the validation case is up to 0.3. So up to 0.3, will the Fourier-Tron precision effect? I don't think that will be too much dominant. If you go
Not
to
really, yeah,
yeah.
because when you have the 0.3, so you have definitely a couple of harmonics,
yeah,
and they will be shifting from your, so they will not be at the position of the frequency associated with the 2-2 mod. That's my point.
Okay, yeah.
We can discuss this offline.
Yeah, sure.
Thank you.
Okay.
Okay, thanks a lot. Any other question? Indulekha?
Yeah, this is just a naive question. Suppose the system was eccentric, but the signal was very poor, so you cannot see those other higher order stuff. So then if you fit, assuming higher order, suppose you fit including all the higher order modes, and without the higher order modes for the noisy data, how close or not close would the two results be?
Yeah, so that's a nice question. So this method has a sort of limitation in the sense that it has to have a sufficiently good in spiral SNRs, at least for the consistency test part. That is why we are projecting this with the A+ noise PSD, where all the in spiral SNRs range in the range of 35 to 65. So you need to have sufficient in spiral SNRs to deal with this, at least with the consistency test part. Otherwise, your grid will be large. You won't be able to constrain or pinpoint with that location.
Okay, thank you.
There is another question from Aditya. Aditya, please go ahead.
Yeah, hi Nirban. Thanks for the nice talk. I was just wondering if this consistency approach, I mean, the time frequency match approach, won't there be degeneracies between, let's say, an eccentricity equal to 0.3 and higher modes, but I mean, with a waveform, let's say, which is, or with a whatever approximate or phenomenological model, which is eccentricity equal to 0, but there are higher modes included. So won't there be a degeneracy between these things?
Yes, so that's a nice question. That is, we are investigating right now. So the thing is, our guess, and in fact, we have tested for a few systems. So if you try to fit among, so you've got a grid, right? And if you try to picking up systems from that grid, if you try to extract energy along those tracks and evaluate the energy, if you have a E equal to 0 higher order mode system, and if you have an original eccentric system, so the energy of that eccentric system will be higher compared to the non-eccentric higher order mode system. So you can actually argue that from there.
I see Gopu, you want to ask another question?
Just a follow-up. I mean, but in that case, the mass ratio will come into the picture. For example, the circular one, if you have comparable masses, those modes will be of much lower significance. Is that going to help?
Yes. Actually, so that will be, whatever you're talking, that will be reflected when we try to fit the tracks and extract the energy. So the energy values will actually capture the information if there is any mismatch due to the fit.
Okay, thank you.
Okay, I see no more raised hands. So thanks a lot, Nirban, and thank you all the speakers in the session. And on behalf of everyone, I'll thank you. Thanks a lot. We will now close the session, but please join in the concluding session, which is at a different link. Thanks a lot, and I'll end the session now.